Hello everybody. So today we will be continuing with our discussions on heat exchanger network analysis. Now, as was mentioned to you that in any particular industrial processes there are a large number of hot streams and a large number of cold streams. When we say a hot stream, it is not defined by the temperature of the hot stream. It is defined by whether the stream has to be cooled or whether it has to be heated. Any hot stream, irrespective of the start temperature, if it has to be cooled, it is the hot stream. Any particular cold stream is that stream which has to be heated, right. So, therefore, we have a large number of hot and cold streams in any process industry. And so, therefore, in order to cool the hot streams and to heat the cold streams, we need hot and cold utilities. What are the utilities that you already know by this time? We had discussed in the last class. Now, if we have to take out all the heat from the hot and the cold streams using cold and hot utilities, then in that case it becomes extremely expensive. We are going to use a huge amount of utilities. This does not also conform to the sustainable industrial activities. So, naturally what we would try to do, we would try to see if by some chance the hot and cold streams can be made to interact through in any particular heat exchanger to exchange the heat between them, and then whatever heat that cannot be removed by this process or whatever heat that cannot be added by this process, that will be provided by the hot and the cold utilities respectively. Now, how do we go about this? Yesterday we had discussed a very simple two-stream problem, right. So, in the two-stream problem, what was that? That was simply one distillation column bottoms product which was used to heat the distillation column feed in a preheater, and that we found was an extremely desirable, or it was an extremely profitable situation, because by that process whatever heat which was supplied by the bottom products was sufficient to heat the feed from its inlet to the desired temperature, and therefore, we could actually eliminate the feed preheater that we found yesterday. Along with that, we found there was also a reduction of both the hot as well as the cold utilities, right. Now, how do we proceed? When we go for an actual problem, there are now large number of streams, large number of hot streams, large number of cold streams. Now, how do we know that whether whatever heat that we have recovered from the hot to the cold streams, that is the optimum, that is the maximum that we can do. We cannot have any further heat recovery between the hot and cold streams within the process, and how to ensure that whatever utilities that we are using after that, that is the minimum possible. Now, for this we cannot just be arbitrary, we just cannot take up any hot stream, any cold stream and try to interact and try to extract the heat by this particular random process. There is no guarantee that we are arriving at the maximum possible heat recovery and ensuring the minimum possible utilization of external utilities. There has to be some particular systematic process. Now, this particular systematic process, this is known as the pinch point analysis, which was already told to you. What is the pinch point analysis that we had discussed in short in the last class? What we do is that for any particular heat exchange, there has to be a minimum temperature difference between the hot and the cold streams, such that we can arrive at a heat exchanger with a reasonable area. If the delta T main is extremely low, then we have to go for a very large heat exchanger, that is not going to be economic, right. So, therefore, what we do based on economics, from where economics come into picture, we are saving on the hot and the cold utilities. But while saving on the hot and cold utilities, we are trying to interact, or rather we are trying to bring into contact the hot streams and cold streams which we are encountering in the entire process. Now, these interactions, they occur in a heat exchanger. So, naturally there has to be some additional capital cost for installing, or rather for these heat exchangers, and there will be some particular savings in the utility, and therefore, an optimum between the two has to be struck, which we had already discussed for a two stream problem in this particular case. I would just like to clarify that when we deal with a two stream problem, the only two things which need to be considered are the area of heat exchange and the utility requirement. I had also mentioned number of heat exchangers because when we are seeing the total composite diagram, then in that case we were also having the condenser, reboiler, etc. But if we just consider the network problem, then it was just the bottoms product and the feed product, and therefore there was just one heat exchanger which was involved in the network analysis. So therefore whenever we deal with a two stream problem, the optimization occurs between the area of heat exchange as well as the utility requirement. And we also found in the last class that both of these, they are function of the minimum temperature difference that has to be maintained between the hot and the cold stream, and this has been defined as delta T min. So therefore this delta T min, it is decided based on economics, and here we find that normally the delta T min, it is 10 degree centigrade or 20 degree centigrade roughly. So usually we take that unless it is otherwise specified. So therefore we find that for this optimization, the single most parameter which have to be considered is the delta T min. And therefore in the last problem, if you find, we had taken delta T min as 10 degree centigrade, and in this particular case, this is the two stream problem. For a specific problem for our case, we had taken the hot stream. Remember, the bottoms product was at 105 degree centigrade, the heat was recovered. After recovery, just check up, it was 81.2 degree centigrade, and then the target temperature, it was 40 degree centigrade. The cold stream was the feed stream which was at 35 degree centigrade, and then after heat recovery, it attained 95 degree centigrade. As a result, normally if the entire heat cannot be recovered, then we also need a heat exchanger to heat the cold stream to the extent which could not be heated by the hot stream. In this particular case, we did not need it. So therefore this was the exact problem that we did. Now since I have already mentioned, delta T minimum is the important thing. So therefore we need to locate this delta T minimum, and accordingly we have to proceed. For the two stream problem, how did we do it? We did it by a graphical technique. What was the graphical technique? We plotted the TH plot. This particular analysis, this is known as the pinch analysis, which we are discussing for the moment. So what we did? We performed the TH plot. For what did we do the TH plot? For the hot stream as well as the cold stream. So the hot stream, it started from 105 degree centigrade and it came down to 40 degree centigrade, and the cold stream was at, in fact here it is not correct, this should have been ST, this should have been TTH. So this was 40 degree centigrade. Cold stream started at 35 degree centigrade and then it ended at 95 degree centigrade, right. So we do the hot stream as well as the cold stream, and then after this what we did, as I had told you, that when we are drawing this, what are the things that are constant? The start and the terminal temperature, the target temperatures are constant. These two terminal points, they are fixed. Sorry, these two terminal points for the y axis, they are fixed. The slope is also fixed. Why? Because the Cp, the heat capacity flow rate parameter, the Cp, which is nothing but m into Cp, this is also fixed. So therefore for this graph, the y coordinates are fixed and the slope, which is 1 by Cp, this is 1 by Cph and this is 1 by Cpc, these are also fixed. But remember, and another thing is also fixed, this delta H, this delta HC and this delta HH, these are also fixed. What is not fixed is the start points, because we know the difference in enthalpy between these 2 points, but what we do not know is that where it starts and where it ends. We just need to ensure that the difference is what has been specified. We need to know that this curve should start and should end at some particular y axis values. The slope should be constant, but the start points, they are not fixed, and they are also independent of one another. This particular fact we exploit in order to arrive at the delta t mean. What we do? We slide these 2 curves horizontally, right. So, therefore, initially maybe the curve was somewhere here. From there we keep on sliding the curve. Normal convention is we keep the hot curve constant, we slide the cold curve till we find that the delta t minimum is achieved. Once this is achieved, we know that we have reached at the optimum, and therefore, this is the maximum amount of Q that can be recovered, and this amount have to be provided by the cold as well as the hot utilities, and these were specified by Q plus and Q minus. This was the thing, right. So, the whole thing boils down to finding out the location of delta P min, which is known as the pinch point, and then from that particular pinch point determining the hot and cold utilities, determining the amount of heat that has to be recovered. From the amount of heat that has to be recovered, determining the area of the heat exchanger. From there we can find out that what is the extra heat exchanger that we have to give, and what are the utility requirements that we have to arrange for this. Now, suppose we come to a multi-stream problem, right. The approach is the same. For the multi-stream problem, what I have done, yesterday we had just discussed a distillation column. Now, today with the distillation column, I have put up a 2-stage reactor. What is the process? I have some particular reactant going into the reactor. From the first stage of the reactor, some reaction has taken place, then it is sent to the second reactor. In the second reactor, from the second reactor, what comes out? The product comes out, and along with that the unreacted reactants also come out. From economic considerations, I would like to separate the two, take out the product and recycle the unreacted reactants back. So, therefore, how do I plan to separate the two? They have got more or less, I assume, sufficient difference in the relative volatility. So, therefore, I would take up the distillation as the process. So, therefore, what I do, this particular stream I introduce into the distillation column. Another additional stream is also introduced into the distillation column from the reactor point. So, therefore, once they come into the distillation column, distillation takes place and we get a top product and we get a bottom product. The bottom product part of it definitely has to be recycled back. We know from the reboiler, this is the reboiler, this is the condenser, and the rest of the portion that has to be cooled and then it is stored or it is taken for some other purpose. So, it goes for some other purpose here. And the top product which is there, the top product actually contains the unreacted reactants. So, therefore, this is introduced once more into the reactor for the reaction to take place. This is the entire thing. So, therefore, what are the streams that are there? One stream is the feed stream, definitely, if we can name it. The other stream which goes from here to here, since I can consider this to be integrated, I do not differentiate the two. Then there is another stream which goes from the reactant to the distillation column. So, therefore, this is one particular stream. From the distillation column, the top product goes out, this is one, it comes to the condenser, then from the condenser there is a reflux and there is the distillate which is again fed here. From the bottom there is one other bottoms product, a part of it is sent here. So, therefore, if I take it as 6 and the remaining part it goes out. So, therefore, this is the 7th stream. So, in total, and well, there is one other I forgot, This is also one stream which is there. Now, out of these total number of streams, through which, see, there are certain streams which do not take part in the heat exchanger network analysis. So, we will be eliminate, or rather we will not be considering them for the time being, but for a total analysis it is important that we consider the heat loads of the condenser, reboiler, everything. For the time being we do not consider this particular stream, we also do not consider this particular stream, we consider this stream, we consider this stream, we consider this stream, and we consider this particular stream. These 4 streams are the streams among which we can have some particular exchange of energy, and therefore, we can extract heat and reduce the amount of utility that is required in order to heat the reactant and also to cool the products of the reactor, and also to heat the condensate before introducing it once more into the reactor. So, therefore, in total there are 4 streams here which we can consider for our heat exchanger analysis. So, therefore, these 4 streams I have written down here. I have slightly changed the numbering, because normally what we do is we designate the hot streams first, we number them consecutively, and then we number the cold streams. This is just for convenience. So, therefore, this is stream 1. Now, for each streams we find that the total enthalpy change during the flow through the pipeline, or rather during the heat exchange, that is provided. Using those, I have calculated the Cp values here. So, therefore, I have identified the streams. First stream is the product from the R2, which changes its temperature from 180 degrees to 80 degrees. So, therefore, stream number 1, this is definitely, it is going to be a this is going to be a hot stream, correct, and this temperature is going to change from 180 degree centigrade to 80 degree centigrade. The Cp is 20. What is the second stream? Then the next hot stream. The next hot stream, this is stream 2, this is the hot stream, this gets cooled from 130 to 40 degree centigrade, right. For this, again, since delta H is provided, I can find out the Cp. The Cp in this particular case is 40. Well, the third stream is the cold stream, because it has to be heated, and it has to be heated from 60 degrees to 100 degrees. So, therefore, this is the stream 3 which has to be, this is the stream 3 which has to be heated from 60 degrees to, this is a cold stream, from the reflux drum which has to be heated from 60 to 100 degrees centigrade. What is the fourth stream? The reactant which comes in. So, this is also a cold stream which is heated from 30 degrees centigrade to 120 degrees centigrade, and here also, since delta H was provided, I can find out the Cp. The Cp is 36, in this particular case the Cp is 80. So, therefore, what I did, the process flow sheet is there. From that I took the data extraction flow sheet, and I just identified those particular streams through which would form my heat exchanger network, and after that I filled up the stream specification table. The same procedure that I had adopted in the for the 2 component case. Now, once this whole thing is there, what is the next thing? I need to construct the hot curve as well as the cold curve. With this particular data which is there, this is the typical stream specification table. Now, the problem is that when I had just one hot stream, one cold stream, it was pretty easy. I just marked the target temperature and the start and the end temperature, and I knew what is the slope. And it is going to be a straight line, because MCP is, or rather the capital Cp, it is constant. So, I could just draw the straight lines. Now, in this case, what do I do? For each particular stream, say for this hot stream, if I take it up, say suppose I start from 80 degrees centigrade and I come down to 180 to 80 degree centigrade, right. So, therefore, for this particular hot stream I can just draw it in this particular way. The slope is going to be 1 by 20. Fine. For H1 I can draw this. Similarly, for H2 it is going to start from say 130 degree centigrade, it is going to end at say 40 degree centigrade. So, for this particular case also I can draw H2, this slope is 1 by 40, that is there, fine, right. Now, these are separate. Now, if I really want to find out how much heat has to be extracted, then I need to draw a hot composite curve. That means, I need to combine these two and draw a single particular curve which will be equivalent to these curves in terms of the slope, or rather it will be equivalent to the total amount of heat which is being interacted by these two hot streams, and the slope will be consistent between the intervals. How do I do this? Now, let me see these two curves. From 180 to 130 I find that there is only H1, right. So, therefore, from 180 to 130 there is only H1. So, therefore, delta H from this 180 to 130, this is simply Cp into 180 minus 130. This is for just stream 1 itself. So, therefore, Cp1, right. So, therefore, for this part definitely I can draw this. Now, from 130 to 80, if you see delta H say 130 to 80, then what is the total heat interaction that is taking place? This is equals to Cp1 into 130 minus 80 plus Cp2 into 130 minus 80. So, therefore, in this particular case the composite curve should comprise of sigma Cp hot, since I am talking about the hot composite curve, into 130 minus 80, which is the temperature difference here. So, therefore, for this particular portion, say this is 80. So, for this particular portion, the straight line that I am going to draw, that should have the slope of say 1 by Cp1 plus Cp2, or therefore, if there are more number of hot curves, then therefore, the slope, or rather this will be shown by sigma Cph, which in this particular case equals to 60. So, accordingly, this particular curve if I draw, maybe this is going to be something of this sort, right. From suppose I take it up from 80 to 40, then what do I get? For this particular portion from say from 80 to 40, what is there, you tell me. From 80 to 40 only stream 2 is there, stream 1 is not there. So, therefore, delta H from 80 to 40 degree centigrade, this will just be Cp2 into 80 minus 40. So, therefore, for this particular case again I draw the hot curve. So, therefore, what have I done? In order to draw the hot composite curve, I have divided it into several intervals. How did I decide the intervals? From the start and the terminal temperatures of the streams. I have divided them considering in sequential order the start and the end temperatures. So, in sequential order it was 180, 130, 80 and 40. Then I have broken them into different intervals. Or for all these intervals, for the first interval this end temperature is the start temperature for the next interval. In this way I have broken it down. Then once the intervals are made, then what I do? I find out the enthalpy changes for each interval. What is the enthalpy change for any particular interval k? It is simply sigma Cp H for all the streams which are there into delta T k, right. In that particular way I have found out the slope, and then this whole thing is done for constant Cp, mind it, all these are straight lines. Accordingly, I have for each particular interval I construct the composite curve. This is the hot composite curve that I have constructed. This, for each portion of this composite curve, gives a single straight line which is equivalent to the total enthalpy change within that particular temperature interval for all the hot streams which exist within that particular interval. So, in this way I have constructed the hot composite curve. I can do the same thing for the cold composite curve. I will be dividing them into intervals. So, what will the intervals be from here? It is very evident. I will start from 120, 100, 60 and 30. So, therefore, this is 120, this is 100, this is 60 and 30. Same way for each interval, what am I going to do? The delta H C for the kth interval, it is going to be sigma CPC delta T K. Same way for this also, I can construct it in the same way. From I find that from 120 to 100 it is just stream 4 which is there. From 100 to 60 I find both stream, so there here only stream 4 is there, accordingly you can construct for 100 to 60 both streams 4 and 3 and 4 are there. Again from 60 to 30 just stream 4 is there. So, accordingly we can construct this. Once both of them are constructed, now in order to find out that whether these hot composite and this cold composite curve, they can correspond or rather they conform to the delta T minimum requirement, which for this problem is specified as 10 degree centigrade. We need to draw both the curves on the same temperature enthalpy plot. So, therefore, for this the entire temperature has to be divided into a large number of intervals considering the start and the end temperature for all the hot and the cold streams. So, in this case it should be 180 to 130, this is the first interval. From 130 to 120, this is going to be the second interval. 100 to 120 to 100, the third interval. Then 100 to 80, this is going to be the fourth interval. 80 to 60, fifth interval. 60 to 40 is the seventh, and then 40 to 30, this is going to be the eighth interval. So, in this way we are going to divide this whole thing. For each interval we are supposed to construct the hot composite curve, which is given by sigma CPH into delta K for the kth interval, and the cold composite curve which will be given by sigma, it is the capital Cp, sorry, sigma CPC for the kth interval with multiplied by delta K. In that particular way we are going to draw the hot as well as the cold composite curves. Now, once these are drawn, just like the single two stream problem, here also these slopes are fixed. The start and end temperatures are fixed. This is the hot composite curve, and just like I had told for the two stream problem, the hot composite curve is always located above the cold composite curve, just to show the feasibility of exchange. So, therefore, these start and end temperatures are fixed. This delta H for each particular segment, that is fixed, but again the start of the two curves, they are independent of one another and they are not fixed. So, therefore, what we do, once we have constructed them on the same curve, then we keep the hot composite curve same and we start sliding the cold composite curve till, see here we have slided it, this was the initial position I drew and then I slided it till I reach the required delta T min for my problem, which for this particular case is 10 degree centigrade, and this is known as the pinch point. Once I have reached this, then I know the location, relative location of my hot and cold composite curves are fine, and they conform to the situation where the maximum amount of heat can be recovered and the minimum amount of hot and cold utilities can be used for this particular arrangement. So, therefore, once this, and this another interesting thing, if you try to bring this curve much more closer such that maybe they both start from the same enthalpy point, you do not think that if you keep on decreasing delta T min you are going to save, because after one point of time you will find that the more amount of the utility you are saving on this side, and equal amount of utility will be opened on the opposite side. So, therefore, this is true for both this side as well as for this side. So, if you are saving on the cold utility, you will be spending more on the hot utility. So, therefore, there has to be an optimum beyond which we do not get any additional benefits in decreasing the delta T min. On the other hand, when we start decreasing the delta T min, quite naturally the heat exchanger area increases, or capital cost also increases. Once this has been set up and we know that at what particular temperature this particular delta T min is honored, then we can go away. What is the next thing that we have to do? We have fixed up everything, and so therefore, now we need to take the individual streams and start matching them and find out that what is the amount of heat exchange that we can have, and what is the number of heat exchangers that we need, and what is the area of heat exchanger that we need. We have to keep in mind that for every heat exchanger, for any particular terminal point, the temperature should not be lower than the delta T min which is specified for the problem, right. So, therefore, before we go for this matching process etc., there are certain other things that I would like to mention before I go to this matching particular part. The first, one thing, if you do it for the problem which has been given, you will find that the hot utility requirement will be this and the cold utility requirement will be this. You can check up for yourself when your delta T min equals to 10 degrees centigrade. You can check it up for yourself. Well, there are certain things that I would like to tell you. We know that whenever we are designing, it is for two stream, it was the area of heat exchange and the utility requirement. When there are more than two streams, then definitely we will be requiring more number of exchanges. So, therefore, when we are designing, what we have to target? We have to target at the minimum number of heat exchange units, the minimum total area of heat exchange as well as the utility requirement. These two, they comprise the capital cost, and this this is the operating cost. Now, a rule of thumb says that the minimum number of heat exchange units in a process which has, say, S number of total process and utility streams. For our case, what is S? We have got 4 process streams, and definitely we will be requiring one hot utility, one cold utility. So, for our case, the total number of process and utility streams is 6. So, therefore, for any particular network, the minimum number of heat exchange units is generally equal to S minus 1, provided there are certain cases under which this is applicable. Firstly is that it is not for the case of no heat recovery. We will definitely not do the problem for that. That means each stream is exchanging heat with the utility. That is ruled out, and when there is exact matching between the hot and cold streams. Both of these, they hardly occur in practice. So, unless these two cases occur, the minimum number of heat exchange units is given by this particular formula. And regarding the minimum overall surface area, what we do? We have already divided our entire temperature interval into a large number of small segments. So, therefore, within each particular segment, we can find out the minimum area by this particular formula, which considers that all the exchangers that we are using, they are counter current flow exchangers, and there is negligible wall and fouling resistance, right. So, for that particular case, when I say counter current flow exchanger, it means that the that the heat exchange which is happening, that is happening in the vertical direction. There is one other thing which I had forgotten to mention, that the range of delta T min, this I had forgotten to mention. What is the minimum and what is the maximum delta T min? Naturally, this will correspond to the maximum overlap and the zero overlap. Zero overlap means when this cold composite curve, it starts beyond the hot composite curve. So, therefore, the range is specified by the maximum overlap as well as the minimum overlap. So, naturally, accordingly we can find out, if suppose definitely all of these exchangers cannot be counterflow exchangers, because whenever we use shell and tube there are some amount of multipassing, and so therefore, in that case you can take FT, and accordingly the exchanger cost, the exchanger cost, it is related to the exchanger area by a power law. So, therefore, the total capital cost for the entire network is given by this particular formula for n min number of heat exchangers with say ns number of shells. So, this is the formula from where we can find out the C network, which is the capital cost, and the what we have found out, that is plotted as curve A here, curve B is the utility cost. So, therefore, just similar to the two stream problem, we can add them up and we can get the cost versus delta T min, from where we find that the delta T min is optimum. Now, if you are really doing a proper heat network analysis, then in the cost analysis it is also important to include the pumping power. When the utilities are higher, naturally the pumping power also goes up. So, normally if you include the pumping power, the graph is shown here. In that case, usually what happens, the delta T min goes up by a small amount. Well, so therefore, we have discussed the stream analysis, or rather the pinch design analysis for a multi-stream problem, and we have used the composite curves for graphically determining the location of the delta T min. Now, this is extremely good for understanding conceptually the problem, but in order to locate this particular pinch point from the graphical considerations, particularly if we have a large number of hot and cold streams, which is something very normal in industries, then this method often becomes cumbersome. And therefore, there is a standard algorithm, the problem table algorithm, which is generally used for finding out the pinch position in a much more convenient way. We are going to discuss this particular problem table algorithm in the next class. Thank you very much.